Hi guys, we're going to talk today about aircraft control surfaces because for some of the lectures that are going to follow, I'm going to assume a certain level of understanding about basic topology, form and function of aircraft. I give these lectures to my first year level students in my 100 level course, but I know that most of you didn't have that course with me. And otherwise, unfortunately, in this aerospace curriculum, you just don't really get a primer on all these things about aircraft. So we're going to spend a bit of time today just talking about what control surfaces are, what the three primary control surfaces are on fixed wing aircraft. So we're going to look at the elevator, the ailerons and the rudder, and we're going to talk about how they work, what they do, and what the sort of pilot does to affect a change to whichever angle, whichever part of the aircraft attitude we're trying to change. So before we speak about control surfaces, it's useful to understand just the very basis of aircraft axes. And so there's a whole bunch of different axis systems that we will be using in aircraft flight mechanics. And I was going to start drawing some diagrams, then I remembered that actually I made a really good set of diagrams on my website. So go to aircraftflightmechanics.com. On the left hand side, scroll down and look for coordinate systems and angles. And on this page here, I've got a couple of useful diagrams that will help you understand the problem that we've got in terms of how we orient an aircraft with respect to the Earth. Fundamentally, we've got something that can move about in 3D space and can be rotated around three different angles. Those angles are pitch, roll, and yaw. Okay, so have a look at this diagram, mainly because I spent a long time creating it and I want you guys to play around with it, but you can zoom, pan, tilt, and look at the different parts on here. Now, the aircraft is controllable in what we call its attitude. And the attitude is the orientation of aircraft axes with respect to either the Earth or what we call a reference trim state. Now, that's a sort of complicated way of basically saying the aircraft attitude defines where the aircraft is pointing. It doesn't necessarily describe where the aircraft is going, because that's different. That's defined by trajectory. But the aircraft attitude is where the aircraft is pointing. Okay, and the way that we affect a change to the aircraft attitude is through the use of control surfaces, and we're going to talk about them today. We'll talk about the ailerons, the rudder, and the elevator. And in fact, this aircraft's missing one side of its elevator. So please have a look at this website because I think it's useful. That's why I wrote it. Play around with these diagrams, and down here as well, also have a look at aircraft aerodynamic angles. I'm not going to talk about these today, but this diagram is quite useful to help you just remember the sign convention of these two. Basically, we've got positive angle of attack is nose up, positive side slip is nose port. Okay, so have a look at these diagrams, play around with them. I think they're useful, and I think they're going to be useful for you guys. So just remember aircraftflightmechanics.com, and just have a look at the other things on this website when you actually get to flight mechanics next year. Let's talk about control surfaces then. So we've said that aircraft control surfaces are there to affect a change in the aircraft attitude. And we'll talk about them with respect to the Spitfire. Okay, so how we affect an attitude adjustment, and we mean literally attitude in terms of its orientation, not the aircraft's demeanor. So we're going to talk about how we do each of these. We've got three directions about which we can rotate. So we've got, let's draw them on here. I'm going to draw aircraft body axes, X, Y, and Z. We've got three directions that we can rotate about. So we've got roll, pitch, and yaw. And we've got the three control surfaces are there to affect changes in both roll, pitch and yaw, but they all do it in a slightly different way, and they all do something slightly different. So we'll go in X, Y, Z. So we'll talk about the control surface that affects the roll, and that is the ailerons. Okay. So the ailerons are parts of the aircraft wing that are basically hinged trailing edges. Now they're there to either be put up or down, thus changing the camber of the wing. Okay, that affect a change in camber. So let's draw a terrible aerofoil, but this, let's say this is a cross section through the wing. Then we would have the aft section would have a hinge section, and that would be my aileron. And this is then adjustable either up or down. Okay, the symbols, we don't really need to talk too much about the symbols, but we'll say aileron deflection, delta E here. Sorry, delta A. Okay, aileron deflection, delta A. You'll see in some older textbooks, and I think maybe in my notes, zeta, eta, and I can't even remember the other one actually. It's another Greek character, sometimes used to talk about the three control surface deflections. I think it's easier to use delta A, delta R, and delta E, which is the American definition. I do prefer this definition. So if the elevator goes down, that's going to increase the lift. And if the aileron goes up, that's going to decrease the lift. We might think at the moment, well, how does that help us on the aircraft? That's just going to, create more or less lift. The reason that this helps us affect a roll rate is because we operate these in differential mode. So if this one goes up, this one goes down. Okay, one goes up, one goes down. Doesn't mean they can only go that way, just that they always work in opposite directions on the aircraft. So let's say, for example, you're flying along in your aircraft and you want to change the attitude of the aircraft such that the starboard wing, the camera's reversed, so I've got to switch this around, such that the starboard wing, yeah, that looks right, such that the starboard wing goes down. Then in order to do so, we would want to to make the starboard wing go down, I'd want to move the stick to the right. Okay, we'll turn the yoke to the right, and then I want to increase the lift on my port wing and decrease the lift on my starboard wing. And in order to do so, trailing edge here would go down, trailing edge here would go up, would affect a roll rate. Let's just write that down because that's important. Ailerons effect Okay, so if you move the stick to the left, that's going to cause the aircraft to continuously roll to the left. Okay, it affects the roll rate, and just for your own learning, that's given the symbol P. Okay, so that's how the ailerons work. Let's move on to the next one, pitch control. Pitch control is affected by the elevator. That is not called a lift in British English, but we're not consistent with the words that we change. Okay, so the elevator is on the Spitfire. It is the aft section of the horizontal tailplane. On some aircraft, you'll see a completely movable tailplane, a completely all movable horizontal tailplane. Now these, again, unlike the ailerons, these aren't independently working in differential mode. These always move at the same direction on both sides. I'm trying to keep this to be a quick video, but this is difficult because how the elevator works is actually a little bit complicated. We could talk about what's called longitudinal static stability for about 3 or 4 hour-long lectures. Basically, the elevator works very similar to how the ailerons work on the wing, but because they're working together, we're either going to increase or decrease the lift that is produced on the horizontal control surface, or the horizontal tailplane. Okay, HTP, horizontal tailplane, pretty standard acronym. So elevator deflection changes the lift that is produced on the horizontal tailplane, and we're not going to get into the detailed complexities of longitudinal static stability, but we can probably appreciate that all of the lift on the aircraft has to be equal to the aircraft weight. Some of the majority is being produced by the wing, some of it's going to be produced by the horizontal tailplane. So these are both producing moments about the aircraft's centre of gravity, which is situated somewhere between the two. If we adjust the amount of lift being produced by both the wing and the horizontal tailplane, then that's going to cause a new trim attitude in terms of pitch to be reached. So elevator adjustment would be affected by pushing the stick forward, would cause the aircraft to go nose down. Pulling the stick back causes the aircraft to go nose up. Same with the yoke. Push the yoke forward causes the aircraft to go nose down. Pull it back causes the aircraft to go nose up. Okay, and this affects a change in pitch attitude. So the ailerons change the roll rate of the aircraft, and once they started, that causes this continuous angular movement. Unlike the ailerons, the elevator causes a change to pitch attitude, and you'll learn all about this in longitudinal static stability, which I really think you should be taught in first year. But yeah, so this makes this change in pitch attitude, and really this just changes the speed of the aircraft. All other things being equal, this changes the angle the aircraft's flying at, changes the amount of lift being produced, and for steady level flight, that really just changes the aircraft's speed. You'll see a variation in altitude as well, but that will generally be short-lived. You can't affect a continuous climb by just pulling back on the stick. If the aircraft is going to climb, the only way you can do that is by putting energy into the system, which is increasing the throttle. Okay, so I want you guys to just think, how can aircraft work? If I push forward on the stick, that's going to make me go nose down. It's probably going to make me go faster. Okay. And so in steady level flight, so this changes speed. And if you've ever flown in a glider, you'll realize the significance of this as well. Okay, so that's the elevator done, ailerons done. Let's talk about the rudder now. So the rudder is the only one that we've not spoken about yet. Let's go over here. And in fact, you'll notice I said the ailerons are hinged sections of the wing, so is the elevator. The rudder is very similar. It's normally just a hinged section of the vertical tailplane or vertical stabilizer. VTP, vertical tailplane. very, very similar thing happens. We can probably appreciate intuitively how the rudder is going to affect a change in the aircraft yaw. What the rudder actually does though, we say that it changes the side slip angle. So we say the mechanism of action is very, very similar. It changes the side force on the rudder. Sorry, not the side force on the rudder, changes the side force on the vertical tailplane. This affects change in side slip, which we give the symbol beta. Okay, so it affects a change in side slip. Rudder is not really used on its own for turning. Okay, you'll learn more about this in aircraft performance. If we want to turn an aircraft in general, we will bank the aircraft, pull back on the stick to increase the load factor, and turn in a coordinated turn. Now we do that in aircraft in general because it keeps the net vector the net force vector on people pointed straight down, which means it feels like we're sat in our seats properly. So you don't ever really feel like you're turning in an aircraft if it's done properly. If we were to use the rudder to turn, they'd be really slow. And we would then feel this centrifugal force pushing us sideways in our seat, which we don't feel. Okay, so that was my quick primer. I've kept that under 20 minutes on aircraft control surfaces, what they're for. They're all there to affect a change in attitude of the aircraft. That's just its angular orientation with respect to either the earth or a reference trim state. They're all hinged sections of either the wing, vertical stabilizer, or the horizontal stabilizer. I've gone through the broad outline of how these all work on traditional aircraft. So we've got ailerons. These in general don't change too much from fancier aircraft. Elevator. This can be either an all movable horizontal tailplane or it can be a hinged section. Some aircraft you'll see that the pitch control is offered through what are called canards. Canards are horizontal control surfaces that are placed at the front of the aircraft. So something like the Eurofighter Typhoon, Rafale or Saab Gripen, those have their pitch control surfaces ahead of the center of gravity. That's there, makes the aircraft unstable, which means it's incredibly maneuverable. Okay, touch upon all of that in your next flight mechanics course. Rudder in general, I don't think there's any aircraft that I've seen with the vertical stabilizer at the front. We need to have the vertical stabilizer at the front or at the back of the aircraft because it gives us what's called weathercock stability, which means the aircraft wants to stay flying in the right direction. And if you can't intuit why that's a good thing, take a playing dart, one of those Nerf balls with a tail on it, try and throw it backwards, like tail first, or like an arrow from a bow and arrow. If you try and throw it backwards, you'll find that it will want to turn over and fly point first, and that's because it's got positive stability when the tail is at the back of the aircraft or when the flights are at the back of the dart, for example. Okay, that was my big primer because we're moving on to control reversal, and I wanted you guys to have an indication of what these control surfaces are, what they do, and how they work. So I hope that's been interesting. We're going to move on to be moving on to control reversal. Like I say, please use that website. I'll keep it up, even when I stop being an academic. I think it's useful for you guys. And if there are any questions, you guys reach out, drop me a message on YouTube, on Slack, wherever, and I will answer all of your fun aircraft questions, or at least I'll try to. Take care, guys. See you soon.